There's an equation, written in 1961 by an astronomer named Frank Drake, that tries to estimate how many civilizations we might be able to hear in our galaxy right now. It's a chain of factors multiplied together. How fast stars form, what fraction carry planets, the odds life gets started, the odds it grows intelligent, the odds it builds something capable of broadcasting, and then, at the very end, one final term, the letter L, how long a civilization remains detectable once it can be heard at all. Drake, and everyone who has worked with this equation since, noticed something uncomfortable almost immediately. Every other term in the chain is debatable, but L swamps all of them. Make life common, make intelligence likely. None of it matters if civilizations simply don't last, because a galaxy full of short-lived civilizations is, for all practical purposes, a silent one. The entire question of whether we're alone collapses, in the end, into a single number nobody has ever been able to measure. How long do they last? And we have exactly one civilization to study, our own, roughly 100 years into being capable of being heard at all. So here's the question worth sitting with tonight. What if the answer isn't very long? We're going to take that final term seriously, and ask whether the thing that ends civilizations isn't bad luck, but something quietly built into what it actually means to become powerful in the first place. Let yourself settle in. None of this needs to be carried with urgency. By the end, you'll understand why the lifetime of a civilization may be the only number in the whole equation that genuinely matters. Why the same window that makes a civilization loud may be exactly the window that ends it. And why the silence we hear out there is precisely what a universe full of short-lived civilizations would actually sound like. This isn't a verdict that we're doomed, but lasting may turn out to be far harder than simply arising, and nobody yet knows whether anything, anywhere, has ever actually managed it. Let's put the whole equation in front of us first, because the argument tonight lives inside one small piece of it, and you can't feel the real weight of that piece until you've seen everything surrounding it. In 1961, Frank Drake was organizing the first serious scientific meeting devoted to the search for alien civilizations, and he needed some way to structure the conversation, a way to break the impossibly large question, are we alone, into smaller pieces people could actually discuss one at a time. So he wrote down a chain of multiplied factors that would, together, give you a number. Call that number N, the count of civilizations in our galaxy right now that we could potentially detect. To arrive at N, you multiply 7 things in sequence. Start with how fast stars are born in the galaxy. Multiply by the fraction of those stars that carry planets. Then the average number of planets per star capable of supporting life. Then the fraction of those that actually develop life. Then the fraction of living worlds that develop intelligence. Then the fraction of intelligent species that build technology capable of sending signals into space. And finally, at the very end of the chain, after all of that, one last number, the average length of time such a civilization remains detectable. How long it lasts. The letter L. The equation was never meant to function as a theory of alien life. It was meant to be honest about ignorance, a way of laying out, clearly, exactly which questions stand between us and an answer, each unknown placed in its own slot, so the entire shape of what we don't know becomes visible at once. That's precisely why it has lasted more than 60 years. We're still using it, still arguing over its individual terms, and still discovering that this one short chain of factors quietly holds the entire problem inside it. Every term in it is really a question about the galaxy. How often does a star light up with planets circling it? How often does one of those planets wake into life? How often does that life eventually look up and start to wonder? And then, at the very end, the question that turns out to matter the most. Once a world has woken up and begun sending its voice into the dark, how long does that voice persist before falling silent again? Here's the thing, hiding inside this structure, and it's the hinge the rest of tonight turns on, so it's worth being careful with it. 6 of the 7 factors are about beginnings. They're about how hard it is to go from a cloud of gas to a planet, from a planet to life, from life to a creature capable of building a radio. Those are the factors everyone loves arguing about, because they feel like the deep philosophical questions. How rare is life? Is intelligence a fluke? And those arguments are genuinely real. But notice what the structure of the equation actually does. The first 6 factors tell you how often a new civilization switches on, how often a new voice could begin, somewhere in the galaxy, and then you multiply that birth rate by L, by how long each individual voice persists. It's that final multiplication that actually decides how many voices are speaking at once. Right now, for us to potentially hear, the clearest way I've found to think about why this one term dominates everything is to picture a long recipe. Imagine a recipe with 7 steps, and you follow the first 6 absolutely perfectly, the finest ingredients, the most precise measurements, the most careful technique, everything flawless. And then the final step says simply, leave to set for the right amount of time, and you pull it out after 4 seconds. It doesn't matter how perfect the first 6 steps were, you end up with a puddle, not a cake. The final step, the setting, carries a kind of veto power over everything that came before it, because it governs whether all that careful earlier work ever becomes the thing it was actually meant to become. L is the setting step. You can have a galaxy that performs the first 6 steps beautifully, reliably, manufacturing stars, planets, life, minds, and radios. And if the last step runs too short, if civilizations simply don't hold together long enough to set, all of that flawless earlier work collapses right back into silence anyway. The final term doesn't merely contribute to the answer. It can quietly overrule everything else in the equation. Think about what that actually means with a simplified version of the numbers. Suppose the galaxy switches on one new civilization every year, a new voice, once annually, somewhere among the hundreds of billions of stars. If each of those civilizations remains detectable for, say, 1,000,000 years, then at any given moment there are roughly 1,000,000 of them out there, talking, because each one is still going while 1,000,000 more switch on behind it. The galaxy would be full of overlapping voices. But now keep the birth rate exactly the same, one new civilization per year, and change only L. Say each civilization lasts not 1,000,000 years, but 100 years instead. Now, at any given moment, only about 100 of them are detectable across the entire galaxy. 100 faint voices, scattered across an ocean of hundreds of billions of stars. Same birth rate, wildly different galaxy. One is crowded, the other is all but silent. And the only thing that changed was L. This is exactly why Carl Sagan, who worked closely on these ideas in the decades after Drake first proposed them, said something that has stuck with thinkers ever since. He said all our arguments about the other factors, all the fierce debate over how rare life is, how likely intelligence might be pale before our uncertainty in L, because the other terms, at least in principle, we can study. We've learned, since 1961, that planets are genuinely everywhere, that most stars host them. We're making real progress on the chemistry of how life might originate. Those front-end numbers are slowly, steadily coming into focus. L is different. L isn't about beginnings, which the universe demonstrates by making new things visibly. all the time. L is about endings, about the eventual fate of civilizations. And we have never once watched a civilization run its complete course, from beginning all the way through to end. We have no examples, none, except, possibly, the one we happen to be sitting inside right now. And that one isn't finished yet. It's worth fully appreciating how much the front end of the equation has firmed up since 1961, because it actually sharpens the loneliness of that final term. When Drake first wrote the equation down, we didn't even know whether other stars had planets at all. Not a single one had ever been found. The fraction of stars hosting planets was pure guesswork. Now, after decades of dedicated observational work and entire missions built specifically to hunt for them, we know that planets aren't rare in any sense. Most stars have them. Our galaxy holds billions of worlds, many roughly Earth-sized, many sitting at just the right distance from their stars for liquid water to exist. One after another, the front-end terms have shifted from total guesses toward genuine measurements, and almost all of them have moved in the generous direction, toward a galaxy rich in planets and possibility. So the overall trend of the evidence has made the early steps look easier, more common, more favorable than anyone originally suspected. Which means that, if the galaxy nevertheless turns out to be silent, the burden of explaining that silence falls harder and harder onto the one term that hasn't moved at all, the one we still cannot measure. The lifetime, the more ordinary the front of the equation comes to look, the more directly the silence points toward the end of the chain. And there's a deeper trap hiding in any attempt to measure L specifically. And it's worth naming clearly, because it shapes everything that follows. With every other term in the equation, you improve your estimate by gathering more examples. Want to know how many stars host planets? Look at more stars. Each new one sharpens the number. But L is the lifetime of a finished civilization. To add even a single example to your dataset, you'd need to watch a civilization run its entire course, from its very first broadcast to its very last, start to finish. We have never done that. We can't do it for ourselves, because we haven't finished yet. And we can't do it for anyone else, because we've never found anyone else to watch in the first place. So L isn't merely uncertain in the ordinary sense, where gathering more data would gradually help. It's uncertain in a much deeper way, where the necessary data is almost impossible to obtain at all, because the thing being measured is an ending, and endings are precisely what silence hides from us. We're trying to estimate the average length of a story, having never once read a single one all the way through. And how long has our own story been detectable so far? About 100 years. We began leaking radio signals into space in the early 20th century. That's the entire span of our existence as something that could, in principle, be heard across the dark 100 years, set against a galaxy more than 13 billion years old. So when we try to estimate L, arguably the single most important number in the entire question of whether we're alone, we're attempting it from one example that's barely a century into a story whose ending we can't see. The data set is one data point, and it's still being written. There's a subtle trap in being that one data point, and it's worth flagging right now, because it casts a shadow over everything that follows. We're tempted to reason, well, we've survived 100 years, so 100 years is clearly survivable, and probably more besides. But that reasoning gets quietly bent by the simple fact that we have to exist in order to ask the question in the first place. Only the civilizations that have, so far, survived are around to wonder about their own lifespan. The ones that ended at year 50 aren't asking anything at all. So our own continued existence can't actually tell us much about how dangerous our situation truly is, because we would find ourselves alive and wondering in exactly the same way, whether long survival turns out to be common or astronomically rare. A creature that has only ever survived cannot conclude much from its own survival, because survival is the precondition for its asking the question at all. We have to carry that humility through everything that follows. Being here, having lasted a century, feels like evidence that lasting is possible, and it barely is, because we're the only ones who could ever have noticed in the first place. It would be a bit like trying to estimate average human lifespan, having only ever met one person, a 100-day-old infant, and being asked, from that single encounter, whether people tend to live for months or for decades. You simply cannot tell yet. The data is one data point, and it's still being written. I find it useful to picture the whole thing as a struck match. A civilization that becomes technological, that learns to send signals into the dark, is like a match flaring to life in a pitch-black room. For a moment, it's bright, unmistakable, visible from across the room, if anyone happens to be looking in the right direction at the right time. That flare is the civilization becoming detectable, becoming loud. And the question the Drake equation forces on us, the question hiding inside that final term, isn't whether the match lights at all. Plenty of matches light. The question is how long it burns before going out, and whether, in that brief lit interval, anyone across the enormous dark room happens to be looking exactly the right way. So if L is the term that decides everything, the obvious next question becomes, why might L be small? Why might the match burn fast? And the first answer, the one almost everyone reaches for instinctively, is the one Sagan himself reached for. Civilizations might simply destroy themselves. Carl Sagan set L at roughly 100 years, and he had a specific reason for it, grounded in something he had personally watched happen, not the ending itself, but the unsettling setup for one. He had lived through the exact moment when a civilization ours first gained the power to be heard across the stars, and the power to end itself entirely, and he noticed that the two arrived almost together. This is the self-destruction hypothesis, the oldest and most intuitive answer to why L might run small, and it deserves serious consideration before we go searching for anything deeper, because it might simply be correct. Picture a single human life spanning it. A person born in the year 1900 would have grown up as radio first, began filling the air with human voices, the first time our species had ever spoken across distances faster than a messenger could ride. That same person, reaching middle age, would have read in the newspaper about the first nuclear weapon detonated in 1945. One life, one ordinary span, from childhood to middle age, and within it, a civilization went from learning to be heard across the entire world to being capable of ending itself in a single afternoon. The two capabilities didn't arrive generations apart, giving society time to absorb the first before confronting the second. They arrived within one person's living memory. The same individual could recall both the wonder of the first broadcast and the dread of the first bomb. That compression, that closeness, captures the whole of Sagan's worry in a single human story, and it's exactly why he set the number so low. Here's the pattern that worried him, laid out plainly. We started broadcasting radio around 1900. Within a few decades, by 1945, we had built and used a weapon capable, in sufficient numbers, of ending our own civilization entirely. 45 years, that's the gap, for us, between becoming detectable and becoming capable of self-destruction, a single human lifetime. A person born when the first voices crackled over the radio could easily have lived to see the first mushroom cloud. The window in which a civilization becomes loud, and the window in which it becomes able to kill itself, didn't open centuries apart. They opened in the same breath, and when you ask why that might be true, the answer turns uncomfortable, because it suggests the link isn't accidental at all. The thing that makes a civilization detectable is mastery over energy and matter. To send a signal across light years, you need to harness serious power, manipulate electricity, build transmitters, command the kind of energy that announces your presence to the surrounding universe. But that same mastery, that same understanding of energy and matter that lets you broadcast, is precisely the understanding that lets you build weapons of enormous destructive power. The knowledge that makes you loud and the knowledge that makes you dangerous aren't two separate things that happen to arrive together. They're the same knowledge. You cannot acquire one without moving toward the other. Becoming audible to the universe and becoming capable of destroying yourself may be two sides of a single step. The analogy that keeps coming to mind is handing a toddler a sharp knife the same day they learn to walk. The problem isn't that the child is somehow bad. The problem is that two capabilities arrive at exactly the same moment: mobility and access to something genuinely dangerous. And the wisdom needed to handle the second hasn't had any time to develop. Because the very same growth that delivered the danger is what delivered the reach in the first place. A civilization in its first century of being loud is exactly that toddler. It has just acquired world-altering power, and it has had essentially no time to develop the maturity to handle it, because the power and the reach arrived in the very same instant of growing up. Sagan looked at that pattern and set L to 100 years, which is to say, he suspected most civilizations don't survive their own adolescence. And he noticed that the knife in the toddler's hand isn't specifically a nuclear knife. That's simply the one we happened to forge first. The deeper worry is that any civilization, as it masters energy and matter, keeps being handed new knives, each one sharper than the last, arriving on roughly the same schedule as its growing reach to be heard. We made nuclear weapons, but the same growth in capability brings the power to alter a planet's climate, to engineer living things, to build machines that act on their own. Each one a fresh way a civilization might end itself. Each one arriving before the wisdom to handle it has had time to grow. So the toddler doesn't simply get one knife on the day it learns to walk. It gets a new, sharper one every few steps, for as long as it keeps growing. And the question of survival becomes whether judgment can ever catch up to a stream of dangers that keeps accelerating. That's the self-destruction hypothesis in its strongest possible form. Not one bad invention, but a permanent and widening gap between what a civilization can do and what it's wise enough to survive doing. There's a useful contrast hiding in the difference between a species and a civilization, and it cuts in an unexpected direction. The typical lifespan of a mammal species, before it goes extinct or transforms into something else, runs to a few million years. So, as a biological species, we might naively expect a long run ahead of us. But a civilization isn't a species. A civilization is a particular arrangement of a species, its institutions, its knowledge, its technology, its social order, and that arrangement is far more fragile than the creatures who make it up. Humans could persist for ages while the civilization, the loud, technological, organized thing, comes and goes, collapses, or transforms into something unrecognizable. The historian and writer Michael Shermer tried to put a number on L using human history itself, taking 60 actual civilizations from the historical record, the ones we have names and dates for, and averaging how long each one lasted as a coherent civilization. The figure he arrived at was roughly 420 years. Now, those weren't technological, radio broadcasting civilizations in the relevant sense, and the comparison is admittedly rough, but the underlying point survives the roughness. Civilizations, the human ones we can actually count, tend to last centuries, not millions of years. They rise, cohere for a while, and come apart. If that's the natural rhythm of the thing, a civilization staying not just intact, but technologically capable and loud for millions of years, would be wildly unlike anything in the only history book we actually have. It's worth pausing on how close our one real example actually came to ending, because it's the only genuine evidence the self-destruction hypothesis has, and it's sobering. In the decades after we built these weapons, there were moments more than one when the whole thing nearly went over the edge, by accident or by misreading. A handful of times during the tensest stretches of the 20th century, early warning systems reported incoming attacks that turned out, on investigation, to be flocks of birds, or the moon rising, or a training tape accidentally left running, or sunlight glinting off clouds. And the only thing standing between those false alarms and a genuine exchange was, in each case, a single human being deciding, on their own judgment, not to pass the warning further up the chain. We don't need to dramatize this. The plain fact is enough on its own. A civilization in its first century of being able to end itself spent that century repeatedly within one decision of doing exactly that, and survived several of those moments not by careful design, but by the simple nerve of individual people. That's the one real data point we have about how a young, loud civilization handles the power to self-destruct. And it isn't a reassuring one. It isn't proof we're doomed either, but it isn't nothing. And it's worth being fully honest about how thin this entire line of reasoning is, because honesty about the uncertainty is the whole point of approaching it carefully. Everything just described is extrapolated from a single case, ours. We have not actually destroyed ourselves. The self-destruction hypothesis isn't an observed law of nature. It's a fear, a pattern noticed in one unfinished example. We came close, arguably more than once, during the 20th century, but coming close isn't the same as proof that self-destruction is the rule. It's entirely possible the danger of those first decades was simply a phase a civilization passes through, and out the other side of that, the toddler eventually grows up. We genuinely don't know. We are one child, still holding the knife, and we haven't yet found out whether we're the kind of creature who puts it down. There's a deeper version of this worry worth naming, because it isn't really about weapons at all. It's about speed. The trouble with a technological civilization is that its power grows on one timescale, and its wisdom grows on an entirely different one, and the two are wildly mismatched. Technological power can grow explosively, doubling and redoubling across mere decades, because knowledge builds on knowledge, and tools improve the tools that build them. But wisdom, judgment, the social and moral capacity to handle power responsibly seems to grow much more slowly, on the timescale of generations, of institutions, of hard-learned lessons absorbed across lifetimes. So a civilization that gains world-ending power within a single century has, almost by definition, not had time to grow the wisdom required to wield it, because wisdom simply cannot be rushed the way technology can. The gap between how fast you can become powerful and how fast you can become wise enough to survive that power may be the single most dangerous feature of the entire transition, and it would apply to anyone. Any civilization that discovers knowledge compounds faster than judgment would face the same lethal mismatch, the same window where it's far more capable than it is careful. So self-destruction is the obvious answer to why L might be small, and it might well be right. But there's a real possibility it's also too obvious, too narrowly human, too much about our particular weapons and our particular politics. It imagines the ending as a choice, a mistake, something a wiser civilization might simply avoid. And that raises a darker possibility, the one that actually unsettles me more. What if the limit on L isn't a mistake a civilization makes at all? What if it isn't a choice, but a trap built directly into the very act of becoming powerful in the first place? What if the thing that ends civilizations isn't war, but something that happens to everyone who succeeds, for reasons that have nothing to do with wisdom whatsoever? The astrophysicist Adam Frank has spent years on a question that sounds strange at first, and then refuses to let you go. What if the moment a civilization starts altering its own planet, simply by using energy on a large enough scale, isn't a specifically human failing at all, but a generic feature of any technological species, anywhere in the universe? Not a mistake we made because of our particular greed or our particular politics, but a phase that anyone hits, on any planet, the moment they get powerful enough to hit it. If that's true, it completely changes the shape of the fear, because it moves the limit on L from something we might simply choose to avoid, into something built directly into the physics of success. Start with an assumption almost everyone carries without quite noticing it. When we think about climate change, resource depletion, a civilization straining the planet that holds it, we tend to think of it as our specific screw-up, a failure of our institutions, our short-sightedness, our particular kind of foolishness, and there's genuine truth in that. But Frank's argument is that underneath the human specifics, something far more general is happening, something that would apply to any civilization made of any kind of creature, on any kind of world. And the root of it isn't psychology, it's thermodynamics. Here's the generic part, and it's unavoidable. Any civilization that becomes powerful does so by using energy to do work. That's what a civilization is. In the most stripped-down physical sense, a system that captures energy and uses it to build, grow, and maintain itself. But the laws of physics are strict about energy. When you use energy to do work, you don't get to use it cleanly and simply walk away. You necessarily produce waste, disorder, what physicists call entropy. And on a planet, that waste doesn't just vanish. It goes into the air, the water, the temperature of the world itself. The very act of using energy at the scale required to build a loud civilization changes the planet that civilization depends on. This isn't a human flaw, it's simply what using energy means, for anyone, anywhere. A civilization of intelligent machines, a civilization of creatures, nothing like us, would face the identical bind because it's a feature of energy and planets, not of biology or character. It's worth making the thermodynamic point concrete, because that's the part that lifts this entirely out of human politics and into something genuinely universal. Every time you use energy to do work, some of that energy is lost as heat. That isn't a flaw in the machine. It's a law, one of the deepest laws there is. You can build a better engine, but you can't build one that escapes this entirely, because the loss of usable energy to disorder is built directly into the structure of physics itself. Now scale that up to an entire civilization. A civilization is, physically speaking, an engine running on a planet, taking in energy, using it to build and grow, and necessarily, unavoidably, dumping disorder and waste heat back into its world as it does so. The more powerful the civilization, the more energy it commands, the more it must dump. And a planet is a closed enough system that the dumping accumulates over time, changing atmospheric chemistry, temperature, the balance of the whole. This is why Frank argues it's generic. It doesn't depend on a civilization being capitalist or greedy or short-sighted. It depends only on the civilization using large amounts of energy on a planet, which is the one thing every loud civilization, by definition, must do. The trap isn't in our nature. It's in the thermodynamics of being a powerful thing on a finite world. There's a way to test this idea, at least within the limited bounds of what we can actually test about civilizations we've never directly seen. You treat a civilization and its planet not as two separate things, but as one coupled system, where the civilization grows by consuming resources. That consumption feeds back onto the planet, changing its conditions, which then feeds back onto the civilization in turn. Adam Frank and his colleagues did exactly this a few years ago, running the model forward across a wide range of starting conditions, many different kinds of hypothetical civilizations on many different kinds of world, to see what tended to happen. In effect, they were asking what fates are common across the full range of ways a technological world might rise and use the energy of the planet beneath it. What it turns up is the part that stays with you. The fates sort themselves into a few broad shapes. In some runs, the civilization grows, strains its planet, and then manages a soft landing, leveling off into a sustainable, steady state, a stable, long-term balance with the world that holds it. That's survival. But in many other runs, the civilization grows fast, overshoots what the planet can sustain, and then suffers a sharp die-off, population crashing hard after the peak, as the degraded planet can no longer support what was originally built. And in a third kind of run, the worst kind, the civilization grows, triggers feedback in the planet that compounds faster and harder than it can ever adapt to, and collapses all the way toward zero. A complete collapse, with no one left. Same basic setup, different parameters, wildly different fates. And a great many of them end badly, not because anyone within the model was wicked, but because the coupled system of civilization and planet is genuinely difficult to steer through the transition without crashing. This connects directly to an idea you may have already heard, the Great Filter. The Great Filter proposes that somewhere along the long road from lifeless matter to a lasting galaxy-spanning civilization, there exists at least one step so difficult that almost nothing makes it past, and that this nearly impassable step is precisely what keeps the galaxy silent. People usually argue about where exactly the filter sits. Is it behind us, in the origin of life, or the leap to complex cells, which would mean we're rare survivors, or is it ahead of us, still waiting? And what the L term suggests, what this entire line of thinking ultimately points toward, is that the filter might be located exactly here, at the lifetime of technological civilizations, specifically, not in getting started, which the universe may accomplish quite easily, but in lasting, which it may almost never manage. If L is the filter, the hard step isn't behind us at all. It's the one we're currently standing in the middle of, the transition from a young, loud civilization into an old, surviving one. And the silence is the sound of almost everyone failing it. That's the darkest place this idea ultimately goes, and it's why L and the Great Filter are, in the end, really the same fear wearing two different names. That's what's meant by a generic bottleneck. The danger isn't a villain. There's no war anywhere in these models. No bomb, no cruelty. There's simply a civilization doing the thing all civilizations do, growing and using energy, and discovering that the planet pushes back, and that steering through the moment when it pushes back is a narrow, difficult passage that many trajectories simply don't survive. It follows roughly the same arc as a gold rush town. A settlement booms around a single rich resource, growing fast and wild in its shadow. And then, when the resource runs thin, or the ground itself is poisoned by the extraction, the boom turns to bust, and the town slowly empties. The same curve plays out again and again in mining towns across the world, not because the people involved were uniquely foolish, but because the dynamics of booming on a finite resource carry the eventual bust inside them, structurally. Frank's argument is that a technological civilization on a planet may follow that same exact curve, and that the curve may be written into the underlying physics, rather than into anyone's character. It helps to be clear about what a model like this is actually for, because people often misunderstand it in both directions. A model like Frank's isn't a crystal ball. It can't tell you what will happen to any particular real civilization, including ours, because it doesn't contain the real numbers, the true strength of the feedbacks, the actual choices any given civilization might make. Anyone pointing at one specific run and declaring this is our future has misunderstood it. But a model isn't worthless simply because its numbers were invented for the purpose. What a good model does is show you the shape of the possibilities, the kinds of outcomes the basic dynamics genuinely allow, the way the underlying pieces can fit together. It's closer to a wind tunnel than a weather forecast. A wind tunnel can't tell you whether Tuesday will be windy, but it reliably tells you how air behaves around a wing, which is a genuinely useful thing to know. Frank's models are a wind tunnel for civilizations. They don't predict our specific weather. They show us how the air tends to move around the wing of a planet carrying a growing technological civilization. And what they show is that collapse is an easy, natural flow, the kind of thing the underlying dynamics produce without anyone deliberately steering toward it. That's worth knowing, even though, or maybe especially because, it isn't a prophecy. It's important to be entirely straight about what these models are and aren't, because it matters, and papering over it would defeat the entire purpose of approaching this carefully. These are simplified models, with parameters we essentially invented, because we have no actual data on real alien civilizations to feed into them. They are not predictions. Critics correctly point out that you can make a model do almost anything, depending on the numbers you plug in, and we don't know the real numbers. So Frank's models don't prove that civilizations collapse. What they do, and this remains genuinely valuable, is show that collapse is a natural, common outcome of the basic underlying dynamics, the kind of thing that falls out of the equations easily, for entirely generic reasons, without requiring anyone to be evil or stupid. They turn self-destruction from a specifically human moral failure into something closer to a physical tendency, and that's darker, because you cannot fix a physical tendency simply by being wiser than the last civilization that failed. So now we have two distinct reasons why L might be small. It might be small because power is inherently dangerous and civilizations destroy themselves directly. Or it might be small because growth on a finite planet is, by its own nature, self-limiting, and civilizations collapse under their own success. Both are genuine possibilities, but notice that both, in the end, remain guesses reasoned carefully from models, and from our single existing example. So let's ask the question a scientist is obligated to ask. Is there any actual evidence, anything we can point to out in the universe itself, that bears directly on how long civilizations really last? And it turns out there is one piece of evidence, enormous, strange, and something we've been sitting inside this entire time. The silence. Here's a fact about ourselves that almost nobody stops to genuinely feel. We've been loud for about 100 years, and we are already getting quieter. The window in which a civilization can actually be heard may be far narrower than the window in which it simply exists. And we are the living proof, because our own loud window may already be beginning to close, only a century after it first opened. There's an image people love telling about this. and it's only half true, which makes it worth correcting carefully. The image is that all our old broadcasts, the first radio plays, the earliest television, are still out there racing outward in an ever-expanding bubble, so that an alien astronomer at the right distance could, this very moment, be watching our oldest programs. The bubble itself is real. Our radio leakage has been expanding outward at the speed of light for about a century now, reaching roughly 100 light-years in every direction, a sphere of human noise a couple hundred light-years across. But here's the correction, and it's the part that actually matters for L. That signal doesn't stay strong. It spreads out as it travels, growing fainter and fainter with distance, until it sinks below the natural radio hiss of the galaxy itself and becomes, for any realistic receiver, fundamentally undetectable. Honest estimates suggest our ordinary leakage would be extremely difficult to detect from more than a few light-years away, even with enormous instruments. So, the bubble isn't a clear, robust broadcast-filling space. It's a faint ripple, fading as it travels, already washed out into background noise not far past our nearest neighbors. The flare is even dimmer and far more local than the romantic version of the story suggests. Think about how we became detectable in the first place. In the early and middle 20th century, we broadcast radio and television by blasting powerful signals out from tall towers in every direction, and a great deal of that energy leaked past the horizon and out into space, radiating outward as a steadily expanding shell of human noise. For a few decades, Earth was genuinely loud in radio, a planet spilling its signals into the dark. That was the flare. That was our match catching a light. But look at what's happening now. We're moving rapidly away from exactly the kind of broadcasting that leaks at all. Signals travel through cables now, through fiber, contained rather than radiated outward. Satellites beam tightly focused transmissions downward at the planet, rather than spilling outward into space. Our communications are becoming more efficient, more targeted, more digital, which, from a distance, means quieter. The very same technological progress that made us loud in the first place is now making us harder to hear. A civilization that has gotten genuinely good at communication wastes very little of its signal into space. People have actually tried to turn our silence into a number 4L, which is a strange and genuinely clever thing to attempt, and the resulting number is sobering. The reasoning goes like this. If you assume the galaxy reliably produces technological civilizations on some fraction of its habitable worlds, then the number currently detectable depends directly on how long each one stays detectable. And since we've looked and found none nearby, you can work backward to set a ceiling on how long the typical detectable lifetime could plausibly be, because, if it were genuinely long, enough of them should be lit at once that we'd likely have heard one by now. A recent analysis along these lines concluded that, given our lack of any detections, the mean lifetime of detectable civilizations is likely under about 5,000 years. That number rests on assumptions you could reasonably argue with about how common civilizations are to begin with, and it shouldn't be treated as gospel truth. But notice what it's doing. It's using the silence, the one piece of genuine data we actually have, to estimate the very term Sagan identified as the most important and the least knowable. And the estimate it lands on is short. Not 100 years, but not the comfortable millions of years either. A few thousand years, roughly the span of recorded human history, and then dark. Now set that figure against the age of the galaxy, because that's where it becomes genuinely vertiginous. The galaxy is more than 13 billion years old. Take a civilization that stays detectable not for mere decades, but for a generous 10,000 years, far longer than our own loud window currently appears likely to last. 10,000 years sounds substantial, longer than the entirety of recorded human history, and against 13 billion years it amounts to nothing at all. It's a flash. If you compress the entire history of the galaxy into a single calendar year, a civilization detectable for 10,000 years would be visible for roughly 20 seconds of that entire year. Strike a match, let it flare for an instant, and that instant is the civilization's entire loud life, set against the long dark night of the galaxy's full history. There's a second way to feel this brevity, and it comes from a stadium. Picture a packed stadium at night, tens of thousands of people, and somewhere in the crowd, a single camera flash goes off. A bright pop, gone in a fraction of a second. If you happen to be looking at exactly that spot, at exactly that instant, you saw it, blinding and clear. But look away for even a moment, and you'd never know it happened at all. Now imagine trying to prove the stadium is full of people purely by catching their flashes, except each person flashes exactly once, randomly, across an entire night. At any given glance, you might see one or none, even though the stadium is genuinely packed. The darkness of the stands between flashes isn't evidence the seats are empty. It's simply evidence that each flash is brief, and they're not synchronized. A galaxy of brief civilizations is exactly that stadium. The flashes are real, the seats are full, and yet almost every time you happen to look, you see only the dark, because a flash is a moment, and the night is very long. This is the second time the match imagery has come up, and now it earns its full meaning. So let me say it plainly. The flare is the easy part, getting the match to light in the first place. Going from a planet to a civilization that can broadcast, as difficult as that genuinely is, as many front-end factors as it requires, is the part that, across hundreds of billions of stars and 13 billion years, probably happens reasonably often. Every match lights, given enough matches and enough strikes. The terror isn't in the lighting. The terror is in how fast the thing burns down. The brevity is the entire problem. A civilization could be as common as striking a match, and the galaxy could still end up dark if the flame simply never lasts. There's one careful distinction worth drawing here, because it's easy to blur, and blurring it would be dishonest. Being detectable and being alive are not the same thing. Everything just described concerns the loud window, the time during which a civilization can actually be heard. A civilization could go quiet, stop leaking signals, become efficient and contained, and still be perfectly alive and thriving for ages afterward, just silent. So a short detectable window doesn't, by itself, prove a short lifespan. It only proves a short flare. The match could go dark to our instruments, while the civilization behind it lives on undisturbed. In fact, the better a civilization gets at everything, the quieter it likely becomes, because waste and leakage are forms of inefficiency, and a genuinely mature civilization wastes very little. So there may be a cruel rule hidden in here. The most successful civilizations might be the hardest to detect, their very competence rendering them silent. If that's true, our search is biased toward catching civilizations exactly like us, young, loud, and wasteful, in the brief, clumsy window before they either die or learn to quiet down. We may be best equipped to detect the ones most like us, which is to say, the ones currently in the most dangerous part of their entire existence. That's real, and I won't pretend the silence directly measures survival. But here's why it still matters enormously, and why it remains the best evidence we currently have. Whether civilizations go dark by dying or go dark by simply going quiet, the result for anyone listening is identical: a galaxy that sounds empty. And that silence is the one piece of actual data we possess about the world beyond us. So let's take the silence seriously as evidence, and ask what it's actually telling us, because we've been listening hard for a long time now, and what we've heard, so far, is nothing at all. More than 60 years ago, for the very first time, we aimed a radio dish at two nearby stars, Tau Ceti and Epsilon Eridani, and listened. To ordinary stars, a dozen or so light-years out, close enough to be worth a try. We were listening for a signal, any signal, some pattern in the radio noise that could only have been produced by a mind. It was the first time we had ever seriously, systematically pointed at another star and asked whether anyone was there. And what came back was nothing. Static, the ordinary hiss of the universe pouring out of the dark around those two stars, and no voice anywhere inside it. That first careful nothing marked the beginning of one of the strangest records we've ever kept, the record of our own listening, and of the silence that has answered every single time since. It's worth being fair about one thing before leaning too heavily on that silence, because it genuinely cuts against my own argument, and you deserve to hear it clearly. The search, enormous as it sounds, has actually covered remarkably little. There's a well-known way of putting this. If you imagine the full search space of SETI, every star, every frequency, every moment in time you'd need to listen, every kind of signal you'd need to look for as a vast ocean, then everything we've actually searched, across more than 60 years, amounts to roughly a single glass of water dipped out of that ocean. One glass. So when we say we've heard nothing, that doesn't mean we've combed the entire galaxy and found it empty. We've sampled a tiny corner of the total possibilities. A confident skeptic could correctly say we've barely begun to look. The silence is real, but it's the silence of having dipped out one glass, not the silence of having drained the entire sea. The silence is genuine evidence, but it should be held loosely. We haven't stopped with two stars, of course. In the 60-odd years since that first effort, called Project Ozma, we've listened with steadily growing power and sophistication, bigger dishes, better receivers, scanning more stars across more frequencies for more hours. Programs have surveyed thousands of nearby stars directly. More recent efforts have swept across billions of stars in the galactic plane. We've searched for narrow radio signals, for pulses of laser light, for the waste heat enormous alien engineering would inevitably give off, for chemical traces of industry in distant atmospheres. And after all of it, the confirmed tally of signals from another civilization stands at exactly zero, not a single confirmed voice. The sky, as far as we've managed to listen, is silent. It's important to be careful here, because silence is slippery evidence, and it's easy to either overinterpret it or wave it away entirely. The silence isn't proof we're alone. It absolutely is not. But here's something worth genuinely sitting with. The silence isn't nothing either. It's real information. An absence can itself be a finding. When a doctor examines a scan and doesn't see a shadow that should be visible if a certain disease were present, that absence is data. It tells them something genuinely real about what is and isn't happening, even though it's the absence of something rather than the presence of it. Our decades of silence work the same way. They're an absence that constrains the available possibilities. The trick, the thing that separates a genuinely useful absence from a meaningless one, is knowing precisely what you would have expected to see if a particular thing were true. The doctor's clear scan is informative only because they already know what the disease would have looked like on it. And the silence of the sky is informative in exactly the same way, but only to the degree we actually understand what a galaxy full of long-lived civilizations should sound like. This is why all the careful theoretical work on what a real techno-signature would actually look like matters so much. The better we understand what we should be hearing, if the optimistic picture were true, the more weight the continued silence actually carries. And on that front, we are slowly, genuinely getting better, which means the silence itself is, in a real sense, slowly getting louder. I want to defend the idea that an absence can constitute real evidence, because people are often too quick to wave the silence away entirely as proving nothing, and that's not quite right either. Think about how much of medicine operates on exactly this principle. A doctor orders a scan, looking for something specific. When the scan comes back clear, that clear result isn't nothing at all. It's a genuine finding. It rules things out. It changes what the doctor believes and what they decide to do next. An absence, in the right context where you genuinely would have seen the thing if it were there, carries real, legitimate information. The trick lies in that phrase, where you genuinely would have seen it. An absence is only evidence to the degree you actually looked in the right place, with sufficient sensitivity to have caught the thing if it existed. And that's exactly the tension running through our own silence. In the directions, frequencies, and time frames we've genuinely searched with enough sensitivity, the silence is real evidence. It does constrain, but we've searched so little of the total possible space that the constraint, for now, remains relatively weak. So the honest position is the careful, middle one. The silence is data. Not nothing, but it's thin data. A clear result from a scan that has, so far, only covered a small patch of the body. It tells us something. It doesn't yet tell us very much. So what does the silence actually constrain? Think back to the equation and the two distinct ways you could end up with a silent galaxy. One way is that the front-end factors are simply tiny, that life, or intelligence, or technology is just incredibly rare, so that almost no civilizations ever arise in the first place. That's the lonely answer, the we are nearly unique answer. But there's a second way to arrive at the exact same silence, and it doesn't require life to be rare at all. You can have a galaxy that easily and frequently produces life, intelligence, and technological civilizations matches striking constantly across the eons, and still end up with total silence, if L is simply small. If civilizations don't last, then at any given moment almost none of them are lit, and the odds that one happens to be both close enough and loud at exactly the same time as us drop to nearly nothing. That second answer, I think, is the one too few people genuinely sit with, because it's in some ways the more haunting of the two. We tend to hear the silence and reach instinctively for one of two comforting stories. Either we're special, the rare ones, almost alone, which flatters us, or we simply haven't looked hard enough yet, and the signal is out there waiting, just around the corner, which reassures us. But the silence is equally consistent with the third story, one that's neither flattering nor reassuring. A galaxy that is, or was, full of life, full of civilizations, full of minds that looked up and wondered exactly as we do, and that we hear nothing from, not because they were never there, but because they simply don't last, because the matches keep going out, because L is small. I want to stay with that image for a moment, because it captures something the cheerful and the gloomy readings of the silence both miss. We argue endlessly about whether the galaxy is empty or full, as though those were the only two options, and as though they would somehow sound different from each other. But a graveyard is full. It's densely, achingly full, more full of the people who once lived there than any living town ever is. And it is completely silent. Fullness and silence aren't opposites in this picture. They're the same place. If civilizations are common but brief, the galaxy isn't an empty field, and it isn't a crowded city either. It's a graveyard, crowded with the traces of the dead, dense with everyone who came before, and silent for exactly that reason, because the crowd is a crowd of the gone. And the strange part is that we wouldn't be able to distinguish that graveyard from an empty meadow simply by listening, because both make exactly the same sound. The only real difference lies beneath the surface, and we can't see beneath the surface from here. We can only hear the silence on top, which the full graveyard and the empty field share equally. A crowded graveyard sounds exactly like an empty field. Both are silent, and from where we currently stand, with the instruments we currently have, we can't yet tell which one we're actually listening to. This entire problem, the gap between how full the galaxy seems like it should be and how silent it actually appears, carries a name. It's called the Fermi paradox, after physicist Enrico Fermi, who is said to have cut through a lunchtime conversation about aliens with a single, simple question: where is everybody? If the galaxy is old and large and friendly to life, it should have filled with civilizations long ago, some of them far older than us, and we should see signs of them everywhere. We don't. That's the paradox. Over the years, people have proposed dozens of solutions to it, entire books worth, but they sort roughly into two families. Either the civilizations were never there in the first place, because the front end of the chain is genuinely difficult, and life or intelligence really is rare, or they were there, and we simply can't see them, for some reason. A small L is the cleanest member of that second family, because it doesn't require life to be rare at all, and it doesn't require any exotic explanation for the silence. It simply says, they were here, and they didn't last, and so they aren't here now. Of all the answers to where is everybody, the one this argument defends is the bluntest. They were here, they are gone, they keep being gone. That's the cleanest way to state what the silence permits. A short L is the single simplest change you can make to the entire picture. The one adjustment that turns a life-rich galaxy into a silent one. You don't have to assume life is rare. You don't have to assume intelligence is a fluke. You can keep every front-end factor as generous as you like. A galaxy that loves making minds and still arrive at our exact silent sky with one single adjustment. Make the civilizations brief. That's it. That one move does all the work, which is exactly why the silence, slippery as it is, points a quiet finger directly at L, at the very term the equation already told us mattered most of all. It's worth being fully honest about the other explanations, because they're genuinely real, and waving them away would make the argument falsely clean. The silence could mean civilizations exist out there but choose to stay quiet, listening rather than broadcasting, hiding deliberately. It could mean they're using some technology to communicate that we don't yet know, to even look for, talking past us in a medium we haven't discovered. It could mean they're simply farther apart or fainter than our instruments can currently reach, and we've only searched a tiny fraction of the haystack so far. Every one of those explanations is genuinely possible, and every one would also produce silence. So the silence doesn't prove a short L, but of all the available explanations, a short L is the one that requires the fewest special assumptions, the one that fits most naturally with everything already discussed about self-destruction and generic bottlenecks and the brevity of the flare. It isn't the only reading available. It's simply the most economical one. So let's try to show what that economical, haunting reading actually looks like. Once you picture not one star or two, but the entire galaxy across the whole of time, all at once, because that picture is the single most vertiginous thing in this entire piece. And once you've seen it, the silence never sounds quite the same again. Picture a dark room the size of the galaxy. Inside it, a few 100 billion matchboxes, one for roughly every star. And picture time, not as the present moment, but as one whole, long night, 13 billion years of it, stretching from the early galaxy all the way to now. Now watch what happens across that night. If civilizations are brief, scattered randomly here and there, a match is struck. It flares bright and clear for its little span. Then it burns down and goes dark. Somewhere else, later, another is struck, flares, dies, and another. Across the whole enormous night, matches are being lit and going out, one after another, scattered through the dark. But here's the thing. If each flare lasts only a moment, compared to the length of the entire night, then almost never are two of them burning at exactly the same time. The everyday version of this that I find clearest is a field of fireflies on a summer night. Imagine a wide field, genuinely full of fireflies, thousands of them, truly full. But each firefly blinks for only a moment, then goes dark for a long while. And they're not synchronized at all, each one blinking on its own private schedule. Now stand at the edge of that field and take a single photograph, one frozen instant. In that photo, you might catch 2 or 3 points of light, or none at all, scattered across a darkness that looks almost completely empty. Someone looking only at your photograph would swear the field was nearly deserted, but the field is teeming. The darkness in the photo isn't absence, it's simply that, at any single instant, almost all the fireflies happen to be in their dark phase, with only a scattered handful mid-blink. The galaxy, under a small L, is that field. And our entire existence as listeners, these few decades, is the single photograph. We're looking at one frozen instant of a field that may have been blinking with civilizations for billions of years, and concluding, from the dark patches in our one snapshot, that the field is empty. It may simply be that we caught it between blinks, and here's the part that makes the field stranger than any field on Earth, because of the one thing light does. When you look out across the galaxy, you're never seeing it as it actually is right now. You're seeing each point as it was when its light first departed, and that light has been crossing the dark for hundreds, thousands, tens of thousands of years to reach you. Look toward the galactic center, and you're seeing stars as they appeared when the first cities were being built on Earth. Look toward the far edge of the disk, and you're seeing light that departed before our species even had a written language. So the single photograph we take isn't even a photograph of one instant. It's a smear of 100,000 different moments, each star showing us a different page of its own past, all of it arriving simultaneously and pretending to be the present. A civilization could be blazing away with signals right now, this very moment, around a star on the far side of the disk, and its light simply hasn't reached us yet, and won't for another 50,000 years. The dark we see isn't even the dark as it currently is. It's the dark as it was layered over itself, every layer a different age of the galaxy, and somewhere inside those layers, the blinks may be happening constantly, just not in any moment we're currently able to see. We're not only looking between blinks in space, we're looking between them in time, at a picture so old, in its farthest corners, that entire civilizations could have risen and gone dark in the gap between when their light departed and when it finally lands on us. That's the picture worth holding, because it's the heart of everything. We tend to imagine the question of alien civilizations as a question about space. Are they out there, somewhere across the distance? But if L is small, the real scattering isn't across space, it's across time. The civilizations are separated from each other, not mainly by light years, but by epochs, by the eras of galactic history they each happen to fall into. One flares and dies a billion years before another is even struck. They're contemporaries of nothing. Each one looks out during its brief moment, sees a dark room, and concludes it's alone. And in the only sense that matters for contact, it is because the others are scattered up and down, a timeline it can never reach. There's a way to feel this that's almost unbearable, in the right kind of way. Squeeze the entire history of the galaxy into a single calendar year. Let the formation of the galaxy mark the first instant of January, and let now be the very last instant of December. On that scale, all of recorded human history, every empire, every name we know fits into the final fraction of the last second before midnight, and a civilization that stays detectable for 10,000 years, far longer than our own flare currently looks likely to be, would be lit for about 20 seconds out of the entire year. 20 seconds, somewhere within 365 days. Now scatter a few thousand such civilizations randomly through that year, each lit for its own 20 seconds. Ask yourself how often two of them would happen to be glowing at the exact same instant. Almost never. You could run that calendar over and over and find, at most moments you happened to check, that nothing at all was lit, and on the rare occasions something was lit, it was almost always alone. That's not an empty year. Things happened all through it. It's simply a year so long, and the flares so brief, that the lit moments almost never coincide. We're checking the calendar at one single instant, our instant, and finding the dark between the sparks. Let me put numbers to it directly, because numbers are what make this land, rather than simply sound poetic. The galaxy is more than 13 billion years old. Suppose a civilization stays detectable for a generous 10,000 years. Then the fraction of total galactic history during which that one civilization remains lit comes out to 10,000. Divided by 13 billion, less than 1 in a million, less than 1 part in a million of the entire night does that single match actually burn. So even if the galaxy produced 1,000 civilizations, or 10,000, or 1,000,000, scattered randomly across all of that time, the chance that any two of them happen to overlap, happen to be lit during the same narrow window, remains small. You could have a galaxy that produced millions of civilizations over its full history, and still find, at any given instant, that almost none are burning at once, crowded across time, empty at any single moment. That isn't a contradiction. That's simply what brevity does to a sufficiently long night. It's worth sitting with the genuine strangeness of being separated by time rather than space, because it's a kind of distance we don't have good intuitions for at all. We understand spatial distance reasonably well. Someone is far away, and if you traveled far enough, you could in principle reach them. It's difficult, maybe impossible at these scales, but it's the kind of barrier the mind can at least picture. Distance in time is different, and worse, because it's absolute. If a civilization flourished in our galaxy 1 billion years ago and then went dark, there's no speed, no technology, no patience that could ever let you reach them, because they aren't anywhere, they aren't far away, they're over. You cannot travel to a time. And the same holds true in the other direction. For any civilizations that arise long after we're gone, who might wonder about us exactly as we wonder about whoever came before, and who will find the same silence, because by their moment, our match will have long since burned out. We are not merely possibly alone in space. We may be sealed into our own private slice of time, with neighbors on both sides before and after, none of whom we can ever touch, because the one direction nothing can travel is across the years. That's a loneliness with no remedy, even in principle, and it's the one a small L would impose on everyone, forever. And that, I think, is the most genuinely unsettling resolution to the silence, more unsettling, even, than being entirely alone. Because being alone, being the only match ever struck, at least carries a kind of bleak dignity to it, a uniqueness. This is worse. This is a universe that isn't empty at all. It's a universe that has been making minds, making civilizations, making creatures that look up and wonder and reach out, over and over, for billions of years. It's simply that they're spread so thin across time that they amount, functionally, to solitude, company that genuinely exists, but never when you do. The loneliness of the asynchronous. Not no one ever, but no one now, no one you could ever reach, because the ones like you are separated from you by the one distance nothing can cross, which is time. And it's worth holding what each of those flares actually was, because it's far too easy to let them blur into abstract points of light. Every one of those brief matches, if this picture is right, was a whole world that woke up, a planet where life crawled out of its own chemistry and spent billions of years slowly becoming something capable of looking up, a species that learned to speak, that built things, that loved and argued and wondered, that turned its instruments toward the sky and asked the exact same question we're asking tonight. Am I alone? Each flare was someone's entire history, their art, their science, their long, slow climb to the moment they could finally be heard, compressed into a single spark that flared and went dark before the next one was struck. The galaxy, under this picture, isn't merely scattered with brief signals, it's scattered with finished stories, each one complete, each one having felt, to those living inside it, like the center of everything, exactly the way ours feels to us. That's what the silence is full of, if it's full of anything at all. Not noise, lives, whole histories that ran their full course in the dark, between our own listening, and that we will never hear, because the one thing none of them could manage was lasting long enough to overlap with us. There's a gentler image for the same idea, and I reach for it because the Matchbox version can feel too bleak to hold, and this one is truer to how it actually works. Picture a summer field at dusk, full of fireflies. Each one blinks for only a moment, then goes dark, then another blinks somewhere else. If you photograph the field with a fast shutter, catching only a single instant, you might see one or two lights, or none, against a field of black, and you could be forgiven for thinking the field was nearly empty. But leave the shutter open for an hour, and the photograph fills with light, hundreds of trails crossing everywhere, because the field was full the whole time. The fireflies simply were never all lit at once. The galaxy under a small L is that field, and we are the fast shutter, catching a single instant. We see the dark between the few visible lights, and read it as emptiness. But the long exposure, the one no one can actually take, the one that would gather all of cosmic history into a single image, might be full of light, crowded with brief blinks, scattered across billions of years. The field isn't empty. We're simply looking with too fast a shutter, for too short a moment, to see that it was always full. This is the match at its full weight, so let me land it. The silence we hear when we point our telescopes at the dark isn't the silence of an empty room. It's the silence of a room where the matches keep going out. 100 billion matchboxes, sparks struck all across the long night, brief flares of light and wonder and reaching, each one going dark before the next is lit. The room was never empty. It has been full of brief fires this entire time. We just happen to live in the gaps between them, as, perhaps, every match always has. There's a question I've been circling without quite landing on, because everything depends on it, and I wanted you to feel the full weight of the silence first. We keep assuming civilizations die young, but has anything, anywhere, ever actually beaten this? Has anything ever managed to last? I'll come back to that, because the honest answer isn't what either the optimists or the doomers genuinely want it to be. The honest answer is that we don't know whether anything has ever lasted, and that's stranger than a simple yes or no, because a civilization that truly endured would leave marks we could find, and we find none, which means either nothing has lasted, or the ones that did are so quiet we simply cannot tell. Survival, if it happens at all, leaves almost the same trace as never having existed in the first place. Let me unfold that, because it's the genuine knife edge of this entire subject, and serious people hold both sides of it. The core of the optimistic case is the idea of spreading out, of not keeping all your existence concentrated in one single place. Almost everything that can end a civilization, self-inflicted catastrophes, planetary collapse, even gamma-ray bursts and dying stars, is fundamentally local. It happens to a particular planet or a particular star system. So the argument goes that a civilization which spreads beyond a single world, establishing itself around more than one star, becomes enormously harder to kill, because no single local catastrophe can ever reach all of it simultaneously. A disaster that would end a one-planet civilization becomes, for a sufficiently spread-out one, merely a tragedy in one place that the rest survives. And a civilization that survives long enough to spread that far would, the argument continues, keep spreading further still, becoming more distributed and more durable over time, until it's nearly impossible to end its existence backed up across so many places that nothing short of the actual death of the entire galaxy could finish it off. That's the vision of a long L, and it isn't foolish at all. It follows logically. If, and this is the enormous if, a civilization can survive long enough and cross enough of the dark to spread in the first place, the immunity comes after the spreading, and the spreading itself requires surviving the very bottleneck we've been worried about, and crossing the very distances we've found almost nothing can actually cross. On one side of this stand thinkers like paleontologist Peter Ward, who argued that the brevity is a phase, not a fixed fate. The idea is that a civilization which makes it through its dangerous adolescence, through its nuclear century and its planetary bottleneck, would emerge on the other side, enormously capable. It would spread its presence outward, no longer dependent on a single planet or star. And a civilization like that, distributed and technologically mature, becomes nearly immune to the things that kill young civilizations. On this view, it could last not thousands of years, but millions, even billions. The match, once it survives its first gust of wind, might be able to burn for nearly indefinite stretches of time. If that's right, L isn't small for everyone. It's small for the young, and enormous for the survivors. And the galaxy might quietly hold a few ancient, enduring fires scattered through it. To see why a genuinely long-lived civilization should be loud, It helps to know what physicists think a truly old one would actually look like. There's a way of ranking civilizations by how much energy they command, proposed by the astronomer Nikolai Kardashev. A civilization like ours, drawing on the energy available to a single planet, sits near the very bottom. The next step up is a civilization that captures the entire energy output of its own star. And the physicist Freeman Dyson pointed out the natural way to accomplish that, by building an enormous structure, or swarm of collectors, entirely surrounding the star to capture its light. We call this a Dyson sphere. And the crucial thing for us is that such a structure could never fully hide. A star wrapped to capture its energy would still have to radiate that energy back outward as waste heat, glowing in the infrared. So a Dyson sphere would show up as a strange star, one giving off heat without the visible light it should otherwise have. This is one of the most actively searched for technosignatures precisely because it's so hard to conceal. Astronomers have combed extensive survey data looking for exactly these infrared signatures, stars that look wrong in the specific way a wrapped star would, and the result, so far, is nothing clear. The very thing a long-lived energy-hungry civilization would almost have to build is the thing we've searched for and not found. But here's the problem with that hopeful picture, and it's a genuinely serious one. If such long-lived, hugely capable civilizations existed, they should be among the easiest things in the entire universe to find. Think about it. A civilization that has lasted 1,000,000 years, that has spread out and learned to harness the energy of stars, would leave marks, enormous structures wrapped around stars to capture their energy, persistent beacons deliberately broadcasting across the ages, the waste heat of titanic engineering glowing steadily in the infrared. These are exactly the kind of long-lived, large-scale signatures our searchers are best equipped to detect, far easier to spot than the faint, brief radio leakage of a young world like ours. A long-lived civilization is a lighthouse, sweeping its beam across the dark, age after age. And a lighthouse is, by design, built to be seen. And when we look for those lighthouses, we find none. No megastructures, no persistent beacons, no Mr. Kabul stellar scale waste heat. Nothing. This is genuinely strange and worth dwelling on rather than rushing past. Studies of what kinds of alien signatures we could actually detect have found something almost paradoxical. The signatures most likely to be found are, in principle, the long-lived ones, the ones that persist for over 1,000,000 years, precisely because something that lasts that long has so many chances to be noticed, sweeping across so much space and time. Researchers including Amedeo Balbi and Milan Herkovic have made this point carefully. If long-lived technosignatures exist at all, they should dominate what we eventually detect, because longevity is exactly what makes a signature findable in the first place. So the absence of any long-lived signature isn't a small detail. It's the absence of exactly the thing we should most easily see if it were genuinely out there. The lighthouse that should be nearly impossible to miss is missing. There's one reading of the silence worth setting on the table now, even though it's the most unsettling and the least falsifiable of all. The possibility that long-lived civilizations exist and are deliberately silent, not out of mere efficiency, but out of fear. The idea, sometimes called the dark forest hypothesis, holds that in a universe where you can never know the intentions of anyone else, and where the distances involved mean you could never defend yourself in time anyway, the safest thing any civilization can do is stay quiet and never reveal its position, treating the galaxy as a dark forest in which the wise predator and the wise prey alike make no sound at all. If that were true, the silence wouldn't mean civilizations are brief. It would mean the old ones learned to hide, that broadcasting, the very thing we did during our own loud century, is a beginner's mistake mature civilizations grow out of, and that the galaxy is full of listeners and empty of talkers. I don't know whether to believe this. It's unprovable almost by construction, and unprovable ideas deserve real caution. But it sits there as a genuine alternative to a short L, a way the sky could be silent and full at exactly the same time. It would be dishonest not to name it, and it matters enormously for us specifically, sitting here at the start of our own loud window. If it turns out that nothing has ever lasted, that the bottleneck functions as a near-perfect filter, then we are almost certainly not the exception, and the honest expectation for our own future runs grim. But if it turns out that some things have lasted, that a long L is genuinely achievable, and the survivors are simply quiet, then the bottleneck is passable, and the real question becomes not whether survival is possible, but whether we will be among the ones who manage it. Those are very different worlds to be living inside, and the maddening thing is that they look completely identical from where we currently stand. The same silence is evidence for both, so we're in the position of someone who needs to know whether the thing ahead of them has ever actually been survived, and cannot find out, because the survivors and the dead have left behind exactly the same empty record. We have to decide how to live inside a question we cannot yet answer, and that, it turns out, is the actual human situation, simply dressed up in starlight. So put the two halves together, and feel the bind they create. Either nothing has ever lasted, no civilization anywhere has beaten the bottleneck and grown old, which would mean brevity is close to universal, a near iron law, and that's the dark reading. Or some civilizations have lasted, have grown ancient and capable, but are for some reason invisible to us, silent by choice, or built in ways we simply cannot recognize, or deliberately hidden, which is its own unsettling thought, a universe of elders who have chosen not to be seen. Both readings are genuinely disturbing in different ways, and we cannot currently tell which one we're living inside. That's the honest answer to the question held back earlier. Not yes, something lasted. Not no, nothing did, but a genuine, vertiginous, we cannot tell where survival and absence leave behind nearly identical traces. The image worth returning to for a long-lived civilization is a lighthouse. A lighthouse is built precisely to be seen, to throw its beam across the dark, year after year, decade after decade, so that anyone passing within range, at any time, will eventually catch it. If the galaxy held civilizations that had lasted 1,000,000 years, they would be lighthouses, their presence sweeping across so much space and time that our chance of catching the beam, even in our own brief glance, would be high, far higher than catching some young world's faint, 100-year flicker. The whole underlying logic of detection favors the long-lived, because longevity is precisely what gives a signal room to be found. So when we look across the dark and see no lighthouses, no steady ancient beacons, no beams that have been sweeping the coast for ages, that absence is louder than the absence of young flickers. It is the absence of exactly the thing built to be impossible to miss. A coast with no lighthouses is either a coast with no keepers, or a coast whose keepers have, for reasons entirely their own, chosen to let the lamps go dark. There's one more turn of the knife here, and it follows directly from the silence already discussed. A civilization that survives by growing quiet, by becoming efficient and contained, and no longer spilling its signals into the dark, would be invisible in exactly the same way a dead one is. Going quiet and dying look the same from across the room. The cost of that is steep. It means survival itself, at least the mature, efficient, no longer wasteful kind of survival, might be nearly indistinguishable from extinction, viewed from the outside. The civilizations that made it might be the quietest of all, precisely because making it means no longer shouting into the void, which would mean the galaxy could be simultaneously full of ancient survivors and full of the dead. And from where we sit listening, the two would sound exactly identical. So we don't know whether a long L is even possible. But suppose it is. Suppose a civilization could, in principle, last. What would actually be trying to stop it? Because even for the ones that beat themselves, the universe isn't finished with them yet. Imagine a civilization that did everything right. It passed through its nuclear adolescence without ending itself. It navigated the planetary bottleneck, learned to use energy without wrecking the world that held it, found the soft landing into a sustainable, steady state. It survived itself, which we've been treating, this whole time, as the hard part. And now comes the genuinely sobering part, which is that surviving yourself isn't the finish line. There is no finish line. Because even a civilization that has beaten every danger it could ever create for itself still lives inside a universe that, on sufficiently long time scales, is actively trying to end it, for reasons that have nothing to do with the civilization at all. Start with a gamma ray burst, because it's the most frightening of these threats, and the most indifferent. When certain massive stars die, or when certain dead stars collide, they release a burst of gamma radiation so concentrated that it's focused into narrow beams, firing outward from the poles. These are among the most energetic single events in the universe since its beginning. If one of these beams happened to be pointed at an inhabited planet, even from thousands of light years away, the consequences would be severe. The gamma rays would tear into the atmosphere and, within minutes, strip away much of the ozone layer, the thin shield protecting the surface from the killing ultraviolet light of the planet's own star. There's a serious scientific argument from researchers including Adrian Mellett and Brian Thomas that exactly this may have happened to Earth, that a gamma-ray burst may have caused one of the great mass extinctions in our planet's deep past, specifically the one at the end of the Ordovician period, hundreds of millions of years ago. A beam, fired from a dying star half a galaxy away, arriving without any warning, at the speed of light, with nothing that could possibly have been done. What genuinely unsettles me about these particular threats is their total indifference. A self-inflicted catastrophe, however terrible, is at least about the civilization, a consequence of its own choices. Something it could, in principle, have done otherwise. A gamma-ray burst isn't about anyone. The star that fires it doesn't know the target world exists. The beam was set in motion by physics that ran its course thousands or millions of years before it ever arrives, aimed at nothing, indifferent to whatever happens to be in its path. There's no malice and no meaning in it, which is somehow worse than malice, because malice at least implies you mattered enough to be a target. A civilization ended by a gamma-ray burst is ended the way a candle is snuffed out by a draft from a door opening in another room entirely, an event that had nothing to do with the candle, never noticed the candle, and would have happened identically had the candle never been lit at all. To last, a civilization would have to survive not only its own choices, but the absent-minded violence of a universe that isn't even aiming at it, and would extinguish it without ever knowing it was there. That's the part that makes these cosmic threats different from self-inflicted ones, and worse in a particular way. There's no choice involved, no mistake, nothing a wiser civilization could have done differently. A gamma-ray burst gives no warning, because it arrives at the speed of light, meaning the light that would warn you and the radiation that would kill you arrive at exactly the same instant. You cannot see it coming, because nothing faster exists to carry the warning ahead of it. A civilization could be doing absolutely everything right, could have solved every problem of its own making, and simply have the bad luck of sitting in the path of a beam fired long ago by a star it never even knew existed, and that would be the end, through no fault and no failure of its own. The Ordovician case is worth sitting with, because it's the closest thing we have to a real example of the universe reaching in and ending a chapter of life for reasons that had nothing to do with the life itself. About 440 million years ago, in the late Ordovician, Earth suffered one of the largest mass extinctions in its history, a die-off that wiped out a huge fraction of the species alive at the time, most of them ocean creatures, since that's where complex life mostly resided. The cause remains genuinely debated, and it would be dishonest to pretend it's settled. But one serious hypothesis, argued by researchers including Mellett and Thomas, is that a gamma-ray burst played a role, the pattern of which creatures died fits, in some analyses, what you'd expect if the ozone layer had been stripped and ultraviolet light had flooded the upper oceans, killing the plankton at the base of the food chain and starving everything above it. We can't prove it. The burst, if there was one, left no crater, no ash layer, nothing but a pattern of death, consistent with a sky that briefly turned lethal. But that's exactly the point. A threat that arrives as pure radiation leaves almost no trace except the bodies, which means we might already have been touched by one of these, once, long ago, and only barely be able to tell. And the gamma-ray burst is only the sharpest member of a whole category of threats. A supernova, an ordinary exploding star, if it went off within roughly 30 light-years of an inhabited planet, could damage that planet's atmosphere badly enough to threaten everything living on it, flooding it with radiation and disrupting the chemistry that protects the surface. We know events like this happen near us. There's a radioactive form of iron, iron-60, produced almost exclusively in supernova, and we find it in the sediments at the bottom of Earth's oceans, laid down a few million years ago. The fallout of a supernova that exploded close enough for its debris to actually reach us. The universe has been setting off bombs in our neighborhood throughout Earth's history. We have simply, so far, been lucky that none has been close enough, or aimed precisely enough, to end us. Add asteroid impacts to this list, the ones that have caused mass extinctions before, and will again, and you have a steady drumbeat of external threats that have nothing whatsoever to do with how wise or foolish a civilization happens to be. I find the iron-60 in the seabed genuinely haunting, so let me dwell on it, because it's the most concrete proof we have that the universe really does reach directly into our own neighborhood. Iron-60 is a radioactive form of iron, produced almost exclusively in supernova, the explosions of dying massive stars. It decays away over a few million years, which means any iron-60 present when Earth originally formed would have vanished long ago. And yet we find it, laid down in distinct layers, in sediment at the bottom of the deep oceans, and in the lunar crust. The most studied layer was deposited a few million years ago. The only way it could be there is if it fell onto Earth relatively recently, in geological terms, meaning a supernova exploded close enough to us, within a few hundred light-years, a few million years ago, and sprayed its debris across the solar system. Some of that debris settled through the oceans and onto the seafloor, where it sits today, a thin radioactive signature of a star that died near us while our ancestors were already walking the Earth. We hold, in the seabed, the physical ash of a nearby stellar explosion. The universe has been setting off these bombs in our vicinity throughout our entire history, and we can hold the proof in our hands. We've simply been far enough away, each time, to survive it. But picture what that means out there. Somewhere within a few hundred light-years of here, more than once, a massive star reached the end of its life, collapsed, and detonated briefly, outshining every other star in the galaxy combined, throwing its outer layers into the dark at a substantial fraction of the speed of light. That shell of debris expanded outward for thousands of years, until it finally washed over the solar system, sleeting through this planet and settling into the ocean floor, where it still sits. The light of those deaths would have been bright enough to see in daylight. Our ancestors may have looked up and seen a new star that hadn't been there the night before, never realizing they were watching the same explosion whose ash we would, one day, pull from the seabed. The asteroid threat is the one we understand best, because it carries the clearest fingerprint in our own past. 66 million years ago, an object roughly 10 kilometers across struck what is now the coast of Mexico, and the dinosaurs, along with most of the species alive at the time, did not survive what followed. That wasn't the only such event. The history of life on Earth is punctuated by these impacts, spaced out across the eons, each one resetting the board. And the thing about an impact is that it doesn't care, in the slightest, about the sophistication of whatever it lands on. A civilization that had cured its diseases, ended its wars, balanced its planet perfectly, and lived in peace for 10,000 years would be just as vulnerable to a 10-kilometer rock as the dinosaurs were, unless it had specifically developed the ability to see the rock coming and move it, which is a capability we're only just now beginning to reach for ourselves. So the impacts are another flood, another threat with no relation whatsoever to a civilization's virtue, arriving entirely on the universe's own schedule, rather than anyone's choosing. The one mercy is that, unlike a gamma-ray burst, an asteroid can in principle be seen coming and deflected, which makes it the one cosmic flood a civilization might actually learn to control, but only if it survives long enough and looks outward hard enough to be ready when the rock finally arrives. The analogy that keeps recurring is a house, and the difference between fires and floods. Most of this conversation has focused on the fires, the dangers a civilization creates inside its own house. Self-destruction, the planetary bottleneck. A careful enough household might genuinely learn to prevent every fire it could otherwise start. But a house that has solved every one of its fires still sits on the land, and the land floods sometimes, from rains that fell far away and have nothing to do with the house at all. The gamma-ray burst, the supernova, the impact, those are the floods. You can be the most careful homeowner in the world, never leave a stove on, never let a wire fray, and still wake one day to water rising through the floor, from a storm you had no part in and received no warning of. Surviving your own fires does not move you off the floodplain. And the universe, it turns out, is one enormous floodplain. There's a common detail people get wrong about the sun, and it's worth correcting, because the real deadline arrives much sooner than the famous one. Everyone has heard that in roughly 5 billion years, the sun will swell into a red giant and swallow the inner planets. That's true. But that isn't when Earth actually becomes uninhabitable. That happens far earlier. The sun is slowly, steadily brightening as it ages, by roughly 10% every billion years. That slow increase is enough that, in roughly 1 billion years, the sun will be hot enough to push Earth past the point where it can hold liquid water on its surface at all. The oceans will heat, evaporate, and be lost to space, and the planet will become a sterilized rock, while the sun is still an entirely ordinary, middle-aged star, billions of years before the dramatic red giant ending everyone pictures. So a civilization on its home world doesn't actually have 5 billion years, it has closer to 1, before its own star quietly turns the planet into something resembling Venus. To last beyond that, it would have to leave to move to another world, or another star entirely, which means crossing exactly the enormous dark we've already established almost nothing can cross. The slowest threat is also the most certain one, and it carries an actual deadline. And then, beneath all of it, the slowest threat of all, the one that comes for everyone who somehow survives all the rest. Stars age, stars change. Our own sun is slowly growing brighter, and in roughly 1 billion years, it will be hot enough that Earth can no longer hold liquid water on its surface. The oceans boiling away, the planet sterilized, long before the sun ever swells into the red giant that will eventually swallow the inner worlds entirely. Some 5 billion years out, every civilization that stays on its home world faces this eventually. The star that gave it life eventually turns on it. To survive past that point, a civilization would have to leave, to move, to cross the very dark we've spent so much time discussing, and we don't know whether that's even possible for anything alive. Even leaving only buys time, because the new star ages too, and the one after that. So truly lasting wouldn't mean surviving one bottleneck. It would mean surviving an unending series of them, staying one step ahead of the deaths of stars, for as long as there are stars left to flee to. So lasting, truly lasting, doesn't simply mean surviving one bottleneck. It means surviving an unending sequence of them. The self-inflicted ones, then the floods, then the slow death of your own star, forever, with no point at which you are ever finally, permanently safe. That sounds like a sentence of doom. It almost sounds like the obvious conclusion is that nothing can ever last. But the same framing that makes it sound impossible, when you turn it around, actually tells us something genuinely useful about what survival would require, and whether it's the kind of thing that can be learned at all. Go back to Adam Frank's models for a moment, the ones that gave us such pause earlier, the coupled simulations of civilization and planet, where so many runs ended in die-off and collapse. The dark half of what they found has already been described. Here's the other half, and it matters just as much. Not all the runs ended badly. Some of them, with the right choices made at the right time, found the soft landing. The civilization grew, strained its planet, and then, before the feedback turned fatal, changed how it used energy, and leveled off into a sustainable, long-term balance it could actually hold. Collapse was common in the models, yes, but the survivable path was always present too. The bottleneck was generic, certainly, but so, within those very same models, was the existence of a genuine way through it. It's worth being specific about what actually separated the surviving runs from the collapsing ones, because the detail is exactly where the hope genuinely lives. In Frank's models, the civilizations that made it weren't the ones that used the least energy or grew the slowest. They were the ones that changed how they obtained their energy before the planet's feedback became overwhelming. In the runs where a civilization kept drawing on the kind of energy source that fed back hard on the planet, degrading the world even as it powered ongoing growth, the collapse arrived no matter what. And worse, in the runs where a civilization recognized the danger and switched too late, the crash still came, because the feedback already in motion played out regardless of any later change. The survivors switched in time, transitioning to ways of running themselves that didn't poison the very system holding them, while there was still margin to absorb the change. So the skill at play isn't exactly restraint. It isn't simply using less. It's a timed transition, a change in the kind of relationship a civilization has with its energy and its world, made during the window when it can still actually make a difference. Miss that window, and even the right change cannot save you. That's sobering and clarifying at the same time, because it says the test is real, and the timing is everything. This is the meaning of survival in a way I find genuinely important, so let me be careful with it. If the bottleneck were pure bad luck, a simple roll of cosmic dice, then surviving it would just mean being lucky, and there would be nothing to learn and nothing to do but hope. But that isn't what the models actually show. They show that the difference between the collapsing runs and the surviving ones isn't luck at all. It's a specific transition, a describable change in behavior made at the correct time. The survivors are the ones who shift from unconstrained growth, consuming more and more, as fast as possible, toward a stable relationship with their energy and their planet, made before the planet forces that change on them through outright collapse. Survival, in these models, isn't a stroke of fortune. It's a skill, a particular, identifiable maneuver that a civilization either performs in time or doesn't. Adam Frank has a way of phrasing this that I find genuinely steadying, even though it changes none of the underlying facts. He suggests we think of ourselves not as uniquely sinful, but as cosmic teenagers. A teenager is someone who has suddenly come into real power, a body that works, a mind that reaches, the capacity to do serious damage to themselves and others before developing the judgment to handle any of it. And the teenage years are dangerous precisely for that reason, the gap between capability and wisdom. But they aren't, for most people, fatal. They're a passage, a hard one, but one that can be come through. Frank's argument is that a technological civilization hitting its planetary bottleneck is a planet going through adolescence, and that the right response is neither the despair of we have ruined everything, nor the denial of nothing is wrong, but the harder, more useful stance of a teenager learning to grow up, taking the danger seriously without treating it as an automatic death sentence. I find that genuinely helpful, because it holds both truths at once. The danger is real. Adolescence kills some people, and the passage is survivable. Most teenagers become adults. Which of those our civilization turns out to be remains exactly the open question, and the framing, at the very least, tells us it's a question, not a verdict. And if survival is a skill rather than a stroke of luck, then our own situation looks completely different than it did an hour ago, because a skill can be understood. A skill can be named, studied, practiced, taught. If what we are going through right now, this moment of straining our planet by using energy at a scale it cannot easily absorb, isn't a unique human disgrace, but a generic transition that every technological civilization faces, then we aren't uniquely doomed, and we aren't uniquely wicked. We're taking a test that, in principle, has a passing grade, a test the physics itself says is passable, even if we don't yet know how many actually pass it. That reframing from moral failure to general transition is genuinely the single most useful idea in this entire subject, because a unique disgrace is something you can only feel bad about. A generic test, by contrast, is something you can actually try to pass. A test has a method. A test can be studied, and a test that others may have failed remains, for whoever is taking it right now, a test that isn't yet over. There's a real lesson hiding in why riding a bicycle is so difficult right up until the moment it suddenly becomes easy. A bicycle is unstable when it's moving slowly, and actually grows more stable the faster it goes, the exact opposite of what fear tells you. Every instinct in a wobbling beginner says, slow down, put your feet down, be careful. And every one of those instincts makes the wobble worse, because stability comes from moving forward with enough commitment to let the balance find itself naturally. The thing that feels safe, slowing down, hesitating, is precisely the thing that drops you. The bottleneck a civilization faces may carry something of this same counterintuitive shape. The instinct, upon realizing your growth is straining your planet, might be to simply stop, to freeze, to cling tightly to what you already have. But the survivable path, in the models, isn't freezing at all. It's a transition, a change in how you move, made with enough commitment and enough careful timing to carry you through to a new kind of balance on the other side. Not stopping, but changing how you go. The wobble and the balance are, in a real sense, the same motion, and the difference is simply whether you lose your nerves somewhere in the middle of it. I don't want to push the analogy further than it can reasonably bear, but the underlying shape of it, that the way through feels exactly like the way down, right up until it doesn't, seems genuinely true to what the models show. There's a stretch right in the middle of learning to ride a bike, where the wobble feels precisely like falling, where every instinct screams that you're about to go down. And many people, learning, do go down, again and again. It genuinely is the hard part. But the wobble isn't the same thing as falling. The wobble is what becoming balanced feels like from the inside, right up until the moment it resolves into actual balance. And you are riding the bottleneck from the inside right now. The strain and the danger and the feedback all feel like the beginning of the end, like falling. And for many civilizations in the models, it is but that exact same wobble, navigated correctly, is also exactly what the transition to genuine, lasting balance feels like from the inside, right up until the moment it becomes balance. The danger and the survivable path aren't two different roads. They're the same road, felt from inside the hardest part of it. I won't oversell this, because the honest uncertainty here remains enormous, and I've promised you honesty throughout. We don't know whether any real civilization has ever actually made this transition. The models show that a path exists in principle, but they can't tell us how likely the survivable path is. Weighed against the collapse paths, whether it's one run in 3 or 1 in 1,000. We don't know if the passing grade is common or nearly impossible. We're still reasoning from simulations with invented numbers and from a single example ourselves that hasn't yet finished its own test. So I'm not telling you survival is likely. I'm telling you something more modest, and I think more useful. Survival isn't obviously impossible, and it isn't obviously pure luck. There appears to be a genuine skill to it, a thing that can, in principle, be done on purpose. And that turns the whole question from a prophecy we're simply waiting on into a problem we actually face, which brings us, finally, to where we actually stand right now in all of this. Because there's one more thing about that final term, the L we've been circling for the better part of 2 hours, that I didn't fully understand until I had walked all the way through everything else. There's something genuinely strange about being inside the very thing you're trying to measure. And it's worth naming clearly. When an astronomer measures how fast stars form, they stand entirely outside that process and simply watch it unfold. They aren't themselves a star. But when we try to estimate L, the lifetime of civilizations, we aren't standing outside it at all. We are one of the things being measured. We are in the middle of our own measurement, and the number we most want to know, our own lifetime, isn't a fact sitting somewhere in the world, waiting patiently to be read. It's an outcome still being produced, partly by what we ourselves do. It's as if the thermometer could itself change the temperature, as if the act of measuring were simultaneously an act of making. For every other term in the equation, we're observers. For this one, for our own value of it, we're participants, and that isn't a comfortable place for a scientist to stand, because it means we can't simply discover the answer the way we discover the other terms. We are, in part, deciding it in real time, without ever being able to step back and see the final result. Because the result isn't finished, and we are the ones still writing it. We've been a civilization that can be heard for about 100 years, and we don't know how long that will last. Think about where that actually places us within the picture we've spent this whole journey building. We aren't a civilization looking back on its own long survival, secure in having lasted. And we aren't yet a civilization that has ended. We're a civilization in the first instant after the strike, still flaring up, the flame not yet steady, sitting at the single most dangerous and most undecided moment of the entire burn. Everything described tonight, the self-destruction worry, the generic bottleneck, the brief flare, the silence, all of it converges on exactly the moment we're standing in right now. We are 100 years into being loud, deep in the part of the curve where, if the dark reading is correct, most civilizations are lost. We aren't observing the bottleneck from outside. We are inside it, in its narrowest part, at exactly the stage where the matches in the dark room tend to go out. That isn't a comfortable thing to realize, but there's a strange clarity in stating it plainly. We are at the dangerous part. We are in it now. That is the entire length of our flare so far. We don't know our own L normally. When a scientist faces an unknown number, the job is to go out and measure it, to find the value already out there, waiting to be discovered. And that's exactly what we do with every other term in the Drake equation. How fast are stars born? Go measure it. How many have planets? Go measure it. Those numbers are facts about the universe, already true, sitting there for us to read. But L, for us, our own L, isn't like that at all. And this is the thing it took the whole argument to truly see. Our own L isn't a fact already written somewhere, simply waiting to be discovered. It isn't a measurement we take. It's a thing we are, right now, in the middle of actively doing. There's a humbling way to see our own position that I keep returning to. We are, as far as anyone can tell, the only experiment in this entire question that we can actually observe from the inside. Every other civilization, if any existed, ran their own version of this test and finished it long before we could ever watch their result already written, already dark. We can't learn from them because they left no record we can ever read. So we aren't merely taking the test. We are, for ourselves, the entire data set on whether the test can be passed at all. A single experiment, still running, with no control group, no prior results to study, no one else to ask. That's a genuinely lonely place to stand scientifically, but it also means something strange, almost vertiginous. Whatever we do becomes, for any later civilization that might one day wonder about us, the way we wonder about whoever came before, the only trace they would ever find of whether a young, loud civilization can grow old. We're writing the one data point we have, and possibly a data point someone else will, someday, try to read. And we're writing it now, without knowing how it ends, which is the only way it has ever been written, by anyone, at all. I keep having to remind myself, and you, how little we actually have to reason from, because it's the most honest thing in this entire subject. One example. That's our entire data set on the lifetime of technological civilizations. One, and it's us. And we're a century into it, and the century isn't over. Everything described tonight, the self-destruction worry, the generic bottleneck, the brevity of the flare, the reading of the silence, all of it is built on top of that single, unfinished example, and a set of models filled with numbers we made up, because we had no real ones to use. I believe the argument. I think the silence genuinely points toward a small L, and I think the bottleneck genuinely looks generic, but it would be dishonest to dress it up as more certain than it actually is. We are one example, recently begun, trying to work out, from our own brief existence, how long such things tend to last, with no other case in sight to compare ourselves against. That isn't a position of knowledge. It's a position of careful, honest guessing. And the most truthful thing that can be said about our own L is that we don't know it, can't know it yet, and are, right now, in the process of finding it out by living it. That's what makes the last term different from all the others, uniquely different. Every other factor in that equation is set by nature, and we're merely spectators reading the result. But the lifetime of our own civilization isn't set yet. We're inside it. We're writing the value with everything we do, or fail to do, in this century, and the ones that follow, if there are ones that follow. The silence out there may well mean the typical L is small, that the typical civilization burns fast. The history, the models, and the bottleneck all lean that direction, and there's no point pretending otherwise. But the typical value is a fact about other civilizations, already finished, already dark. Our value isn't finished. Ours is the one number in the entire equation that isn't a measurement, but a choice still being made. The only term whose value, for us, is at least partly in our own hands. It's worth being careful not to turn that into a cheap inspirational line, because it's genuinely heavier than that. Partly in our own hands doesn't mean fully in our control, and it doesn't mean survival is likely. The cosmic floods are still out there, entirely indifferent to anything we decide. But the part that is ours, the part about whether we navigate our own bottleneck, whether we manage the timed transition the models suggest is genuinely possible, that part remains undetermined, genuinely open, genuinely still being written, by what a civilization does within the window it happens to have. Most of the equation is a report on a universe that already simply is. This one term, for us, is a question still being answered, and we are the ones answering it, whether we attend to it or not. And that, I think, is the strange place this entire argument finally arrives at. And it's where I want to leave you with what I genuinely believe it means. Here's what I keep coming back to. We started with an equation, and with a single term inside it that nobody can measure. And I've spent this whole time explaining why that term, how long a civilization lasts, might be small, might be the very thing almost nothing survives. And I believe that's a real possibility. The silence is real. The bottleneck looks generic. The universe does seem to keep making light, and watching it go out. But there's one thing about that term that's different from every other number in the equation, and I didn't see it until late in working through all of this. Every other factor is a fact about the universe that we go out and measure. How many stars, how many planets, how often life begins, they're already true, and we're merely reading them. The last term, for us, isn't like that. We're still inside it. Our own number isn't finished. It isn't a fact we discover. It's a thing we're doing right now, in the only century we've so far been able to be heard. So I think the terror and the hope are, in the end, the same fact, seen from two different sides. No civilization may ever survive. Or everyone who does is a civilization that decided to. We are a match that has just been struck. We don't know how long the flame lasts, and nobody is going to tell us. But the one thing a flame gets to do while it's still lit is give light, and ours is lit right now. Sleep well.